extending now the same problem to a double pendulum problem. Okay. So what is given? Again, it's an initial value problem. Let's say torque acting at the joint AN between the ground and the first link is given, and torque at joint AB or BA acting on the body B is also given. Initial angular positions theta A, theta B are given, and theta A dot, theta B dot are also given. So we are required to find theta A, theta B, theta A dot, theta B dot for a specified, like basically solve the equation of motion for a given time span. Okay. So there are three bodies, N, A, and B, and NA number of points are 1, 2, 3, 4, 5, 6, 7 points. NA, NB, AN, AO, AB, BA, and BO. NO, AO, BO, as before, are all center of masses, and the coordinates, the body fixed coordinate systems are as shown in the figure. Okay. So we have to make and theta A and theta B are the two generalized coordinates or 2 degrees of freedom of the system. Okay. Now transformation matrices, just like for the simple pendulum problem, you have a transformation matrix between body N and A, again between the ground and B, N underscore A and N underscore B. Okay, the local vectors. So now here there are three local vectors which are of interest. Vector from AO to AN expressed in body A is given in the slide. Again from AO to AB, the second one, and BO to BA also expressed in body B in the local coordinate system. Okay. So now position analysis, you simply have, before doing the position analysis, we will first determine the capital R vectors, which are same the local vectors but are expressed now in the ground fixed coordinate system. Okay. You have the position analysis, which is basically determining the coordinates of all the points of interest. So all of these are points of interest. So we will determine the positions using these equations. Okay. Once that is done, then we can do the velocity analysis. You have omega A and omega B, which is 0, 0 theta A dot, 0, 0 theta B dot, and then you do the velocity analysis. Velocity of AO is VAN plus omega cross RAN, so on and so forth. So this is like a chain. Okay. So these are equations set 2, right? We have given a number. So now these velocities can also be written in terms of the Jacobians as omega equals to J times theta dot. So as many, you have two generalized coordinates, so it is summation of two terms. So for all the angular velocities and also the linear velocities, this can be written. The superscript just indicates the number of the generalized coordinate, but not JA2 is not the square. The superscript does not indicate square, it is index. Okay. Okay. So these vectors, the Jacobians, can simply be computed using theta A dot equal to 1 and theta B dot equals to 0. So if we have written a subroutine for the velocity for equation number 2, the whole set of equations, you simply pass theta A dot equals to 1 and theta B dot equals to 0 to that subroutine to get J1s, and to get J2s you do the reverse. Okay, so now again accelerations, same process as before, as we did for the simple pendulum and simple pendulum. So you have alpha A, alpha B, omegas are already known. So you here theta dot, theta A double dot and theta B double dot are unknowns. But first let us write the equations, and again those equations can also be written as, in this form, just like we did for the simple pendulum problem. So the Jacobians you have already determined using in the velocity analysis, and now you have a omega components, which we can see here, the omega components of all the accelerations, which can be determined by simply putting, so writing again just like velocities, you write a subroutine for just to compute the accelerations of all the points of interest, and then you pass omegas and theta double dots equals to 0. So the omega components of acceleration can be computed by simply putting theta a double dot, theta b double dot equals to 0 and passing the r's and the omegas to the subroutine which does the acceleration analysis. Okay. Now, if you write the Newton-Euler equations, force balance and moment balance equations, so you have sum of all the forces acting on body A to be 0. So the gravity force, the reaction force at AN and AB, and the inertia force, which is mass times acceleration AO. Okay. And then you have the moment balance. Always moments we are taking about the center of mass. So you have TA, which is the net torque acting on body A, and R cross F for both the reaction forces, and I alpha. Okay, same for body B. Okay. Now, if we write in these equations, we have alphas and accelerations. So from our acceleration analysis, you write the accelerations in generalized form, which we have seen before, and then theta a double dot and theta b double dot are the unknowns. Okay, so if we substitute theta a double dot, theta b double, these alphas and a accelerations in the Newton-Euler equations, and then writing them in, rearranging them, and now everything that is marked in red is the unknowns. So how many equations do we have? The first equation here is the force balance equation. So this is two equations along x and y. The third equation is the moment balance equation. It is just a single equation. It will turn out to be a single equation. And again here you have two more and then one more. So total 6. And then number of unknowns. FAN has 2 components. FAB has 2 components. So that is 4. And then you have theta a double dot and theta b double dot. 5 and 6. So 6 unknowns, 6 equations. So you can write this in matrix form. So once we do that, we have AX equal to B form, where A is given over here and B is given there, and X, which is a vector of unknowns, is also given on the slide. So you simply invert, do the inversion, matrix inversion, and we can solve for all the reaction forces and theta A and theta B. This is if we follow the Newton-Euler equations. Okay. If we use Keynes method, which is based on principle of virtual power or Jordan's principle, we write, the sum of total virtual powers to be equal to 0. So there will be 2 equations, one for the first generalized coordinate, which is theta a dot, to the second equation for theta b dot. Both of them will include all of these terms, total 1, 2, 3, 4 and 8 terms. Okay. So this is total power, virtual power for each of the forces that are acting on the system. So we don't take into account the reaction forces because we are looking at the entire system as a whole. Okay. So your external forces on the entire system is the torque, net torque A and net torque B, force of gravity on both the bodies, and then you have the inertia force, which is minus ma on both the bodies, and inertia torque minus I alpha on both the bodies. Okay, sum of all of this is 0, and each of these dot product with the corresponding velocities. Okay. So from velocity analysis, we have written omega A as j theta dot summation, same for omega B, and velocity also, velocities of the 2 points AO and PO. So now from this, if you do the partial with respect to theta a dot, we get JA1, JA2, and you can substitute this in the Keynes equation, generalized form of the Keynes equation. So this is how you have the final equation. The difference you can see is that this is very symmetric, okay. So this is the equation. Now, for acceleration analysis, from the acceleration analysis, we have written acceleration of center of masses in terms of j theta dot and the omega component, which can be computed. So we also have alphas written in this form, right? Okay, so now again, if we substitute the accelerations and alphas in the Keynes equation, so we get this, and rearranging and identifying the unknowns, which is basically theta a double dot and theta b double dot, we get, okay, it's all, again we are rearranging the terms, taking out theta a double dot, theta b double dot. Okay, we're still working with the general equation where I equal to, simply if we put y equal to 1, it will be the first equation of motion. If we put I equal to 2, we get the second equation of motion. Okay, now we're writing both of them separately. You can see that they are very symmetric. Okay, so the final equation is simply a 2 by 2 matrix, J matrix, which is filled with the dot products. So this is your J and K. So your J components, or the components of the 2 by 2 matrix, are simply the inertia forces, you can see, multiplied with the corresponding Jacobian, and your K components, which is on the other side of the equation, are the applied forces and the omega component of the inertia forces. Okay. So this can be easily extended to solve equations of motion of an n-link open kinetic